Okay, what we're doing today is continuous functions. Continuous functions is sort of a big theme, so we're going to break it down into two lectures. I think what we will do today we will give an intuitive definition. We will meet some of the most famous discontinuities. We will give a rigorous definition of what it means for a function to be continuous. We'll check some of the standard type of question or reasoning, like checking if a function is continuous at a certain point. And we hope to go through a lot of examples. If we do that today, we'll call it a good day. This is sort of just the meeting of the continuous concept. Once we meet it today, what we want to do next lecture is maybe explain why it's such a big deal. It is a big deal for some reasons, and I think that's why we're going to break it up into two lectures. So that's our game plan for today. We got to explain continuous functions. Okay. So here's how it goes. This is an intuitive approach. We will say that f is continuous at some point. By the way, this part is important. Usually you'll say at some point or on some interval, and if that's left out, you mean continuous everywhere. But let's just start off at a point. F is continuous at a point 5 if, among other things, there's a little tiny neighborhood around 5 where the graph can be traced without lifting your pencil. Now, what exactly does that mean? Compare these two graphs. So compare these two graphs. Suppose you've got some function here, f of x, and f of x is going this way, nothing out of the ordinary, some function such as that. And suppose you've got the point here, x equals 5, and suppose you're checking to see this condition. F is continuous at 5 if around 5 there's a little tiny neighborhood. How tiny? Well, as small as you want it, where the graph can be traced without lifting your pencil. And so you look at the little tiny neighborhood around 5 on the graph. So you go up 5 so this is 5. This would be a little tiny neighborhood around that right there. That would be a little tiny neighborhood around 5. The question is, could you trace it there without lifting your pencil? And let me see, as you try to, let's close this little thing. So as you try to trace it to see if you could trace it around there, let's see, without lifting your pencil. I did it without lifting my pencil. So that's a nice property to have. So when the function continues, you must be able to trace it without lifting your pencil, at least around that tiny little neighborhood. Compare that with the following graph. Suppose you had some other function and it went something like this. It goes like this, and then it has an empty spot there at 5, and then the function picks up a couple units above it, and then it keeps going as if nothing happened. Now here, no matter how hard you try to trace it without lifting your pencil, no matter how small of a neighborhood you pick, and you try to trace that without lifting your pencil, you're going to go like this, and then you have to lift it and then pick up over here and finish the trace. You can't do it. You got to trace part of it, lift it, and then trace the other part of it. So that right there, that's not something we want when we want our functions to be continuous. So among other things, one of the things you can do when the function is continuous is you can trace it without lifting your pencil. By the way, this is a famous type of discontinuity. This is called a jump discontinuity. So we're going to have to learn the language, the verbiage here. That right there is called a jump discontinuity. And it's famous. When functions were first invented or talked about, or even when calculus was invented in the late or middle 1600s, all functions were nice like this. They were all nice and continuous. They didn't even need to talk about continuous functions. The need to talk about these continuous functions these ones didn't even pop up on the radar till a couple hundred years later, in the late 1800s, when Fourier was analyzing heat flow equations in physics and whatnot. These sort of non-continuous functions started popping up all over the radar, and all sorts of applications. And so then we had to go back. They had to go back and rethink what it meant for continuous, and all these theorems that they had developed. They had just assumed everything was continuous. They had to go back and retweak them to account for the strange things that can happen, like this jump discontinuity. But that's not all. Here again, something else could happen. Even if it's not that bad, something else could happen. Again, here's a function. Here's 5. You could pick a little neighborhood around it, no problem. It could be traced there. It could be traced without lifting your pencil. The other one could be a little bit less problematic, but now in this case the graph there's no jump discontinuity. It seems to be fine. If you approach it from the left, from the right, everything's nice. But still, if you were to make a little neighborhood around it, there's no way you can trace it without lifting your pencil, because there's nothing there to trace. The graph could look like that where it has a hole, or it could look like that where it has a hole and the function still defined but not defined on that point. And so something like this you cannot trace without lifting your pencil. That's one of the criteria. If you want to be continuous, you should be able to trace it without lifting your pencil. And in fact, this type of problem here, this type of discontinuity has a famous name. This is called a removable discontinuity, and it has a key feature that you could just remove it by covering one little point. If you can fix the problem with one finger here, it's removable. In other words, if you could cover up the problem with one finger, or maybe you need a finger like this to cover up the whole problem. I don't know, whatever. But if the problem is a one-point problem, if it wasn't for that point, the graph would look really, really nice like this one. Then you've got a removable discontinuity. And algebraically, what that looks like is possibly something like this. It could look like this. Let me think. Let me erase that. Algebraically, what that could look like would be something like this. Y is equal to, say, x squared times x plus 3 all over x plus 3. Where really this function just looks like x plus x squared. Except at the point where when x is equal to 3, you have an undefined function. You try to plug in x equals 3 and you get 0 over 0, which is not defined, so you inevitably have a hole on that function. If you try to graph this on a graphing calculator, I don't know, some graphing calculators don't have a clue, or not programmed to look at things carefully, but it really should have a hole on the graph here at x equals 3, because it's not defined at x equals negative 3. So anyways, algebraically, this is what they look like when you can remove them. You can just remove them. That's why they're called removable discontinuities. And I'll talk more about that later. But I'll really talk more about that later. Anyways, this is a famous type of discontinuity, removable discontinuity. And the other one was famous. It's called jump discontinuity. But wait, there's more. If a function is to be continuous at 5, among other things, you should be able to make a little neighborhood around it and trace it and keep those numbers real. Okay? You should be able to trace it and keep it real. Now, what exactly do I mean by that? Consider this example. Suppose you have an equation, and suppose that equation has a vertical asymptote at 5. This is x equals 5. And suppose the equation goes like this, and suppose it goes like this, and it gets infinitely close. Now, if I pick a neighborhood around 5, there's no way I can trace that without keep it real. You can't keep it real, because if you start to trace that and you keep tracing it, how far do you have to go up? Well, you'd have to go up all the way to infinity. and you'd never really get there in real time, so to speak. And so this is going to go off to infinity. This is not real. This is called famous name for this. This is called an infinite discontinuity. And it's also famous. Infinite discontinuity. They have asymptotes. They could go either this way, or they could be the ones that go in opposite directions. Either way, you're not keeping it real when your functions go up there. We would call it discontinuous at the point x equals 5, right? Super famous. This is called infinite discontinuity. Alright, there's more. When you have a function, you should be able to trace it without lifting your pencil. Already we did that. But more than that, you should be able to trace it without running out of pencil lead. Now, what exactly does that mean? See, these things are crazy. They tell you how crazy these functions can be. So, for example, there's a famous function. The famous function is... where is the famous function? Disappeared. I'll write it for us. The famous function is y is equal to sine of 1 over x. Now we all know the sine graph goes more or less like this, right? The sine graph. But as you get closer here, imagine what's happening. As the x gets closer to 0, this is getting larger and larger. For example, from say 0.1 to say 0.001, it's gone from, if you invert it, it's gone from 10, from sine of 10 radians all the way to sine of 1000 radians. In this period, it has gone from sine 10 to sine 1000. You know how many times it's gone up and down? Imagine spinning from 10 radians, which is a little, approximately 3 pi, all the way to 1000 radians from here to here. So it has gone infinite many times, or many times. And from there to say 0.000001, it'll go even more times. So it gets closer and closer and closer and closer, infinitely. The period keeps getting smaller and smaller and smaller, to the point where strange things are happening here. If you were to try to trace this, you would indefinitely have to trace it an infinite length. You'd be tracing all day and all night and forever and ever, and you wouldn't finish tracing it because it goes on forever. And in real time, it doesn't get there not until you get to infinity. So that's what I mean when I say you should be able to do it without running out of lead. If you try to trace this, you're going to run out of pencil. But I never thought about this. This never runs out. It's got no lead. Anyways, you know what I mean. You see, that tells you the nuances of explaining what continuous is. It's so, there's a lot of little details that you have to think about. And the problem is that discontinuities could be so crazy. This is called you guys know what type of discontinuity this is? We already saw infinite discontinuities. We saw removable discontinuities. We saw jump discontinuities. What kind of discontinuity is this? This is called a crazy discontinuity. Crazy. And there's many more where this one came from. The discontinuities can get so strange that we'll never be finished describing those. But I should probably give you one more example of this. I think the books really don't call it crazy discontinuities. I think they call them irregular discontinuities. Maybe one more example. This is a famous one. It's called the Derelict Function. Derelict Function, and it says that the f of x is either 1 or negative 1. 1 if x is a rational, and negative 1 if x is real but not rational. And when you see rational, you should just be thinking about fractions, okay? Like 1/2 is a fraction. It's a fraction with integer on the top and integer on the bottom. If that happens with a non-zero on the bottom, we call that a rational. Just a fancy name for saying, you know, regular fractions. Then it would go to 1. But okay, and at 1 it would go to 1. At you know, 3/4, that's a regular fraction, it would go to 1. At 1/4, it's a regular fraction, it would go to 1. And you see, well, it all goes to 1. Well, no, not really. It turns out that between 0 and 1/4, there are things that cannot be written as a fraction. For example, I'm going to make this red. For example, 1 over the square root of 5. That one, no matter how hard you try, you cannot write it as a regular fraction with integer on the top and integer on the bottom. This is not an integer, by the way, it's square root of 5. So that one would have to go to -1. And between here and here, we can also find some more. For example, 1.5 over the square root of 10. That would be in the middle, and it would go, and you cannot write it as a fraction. And so between every one of these, you can find an irrational. You see. And then not only that, but it gets worse. Between every 2 fractions, you can always squeeze an irrational. And between every 2 irrationals, you can always squeeze a fraction. You know, an integer. So in the end, it's going to look like a bunch of dots here, infinitely tied together. And between every one of those dots, there are, of course, dots over here. And so this is all -1, and this is all +1. So this thing is like this, and it is so discontinuous. I can't tell you how discontinuous this is. It is really ridiculously discontinuous. That's how discontinuous it is. Because think about it, every single place where you try to trace it without lifting your pencil, you can't even go one little number or one little piece infinitely small. You can't even go before you have to jump down here, and you can't finish tracing it. And if you try to trace it over here, you can't even go one little number before you have to jump back over here. So it's impossible to trace without lifting your pencil. Yeah, this is ridiculously discontinuous, and it's one of the famous examples that everybody should get to see. And interestingly, you know, there's a lot more going on here. These numbers right here, the rationals, there's infinite many of them between 0 and 1, but they're countable. You can actually count them. These other ones, there are also infinite many of them, but there are so many more of these that they're not even countable, which is a huge paradox, because we said between every 2 there's one of these ones, and between every 2 of these there's one of those. So you would think maybe there's 50-50, right? Wrong. There's so many more of these. There uncountably many. Cantor is one of the great thinkers that did a lot of work on this subject. He showed how uncountable sets. He showed one of the most elegant proofs to show that certain sets were uncountable, and this underlined the distinction between different types of infinity. Amazing. So this is an interesting question for you. Is there 50-50, 50% here, 50%? No, there's a lot more of these. Well, how much more? It turns out that really, if you were to make any sort of sensible measurement, there would be about 0% there, and there would be about 100% there in the 100 bucket and in the 0 bucket. I know, huh? It's amazing, but that's what you would learn in a standard measure theory course. All right, so that gives us a preview of some of the most famous discontinuities: the irregular ones, the infinite ones, the jump discontinuities, and the removable discontinuities, famous discontinuities. And that gives you a good intuitive notion of what it means to this. Let me see where we're at on that. This gives you a good intuitive notion of what it means to be discontinuous. Examples of famous discontinuities. What we have to do now is we have to cut this out. That's enough of intuitive notions. We gotta provide the rigorous definition of continuous, and then maybe practice checking for continuity. I already gave some of the most famous examples, so this is what we got to do now. Like I said, this notion of continuity, it took hundreds of years, even after the discovery of calculus, to put it all nice and tight and put it all right. It was Bolzano, a Catholic priest who did work in the late 1800s, who said, hey, you know what? We really got to check these things. We got to prove them. And so the work started to make this super rigorous, very, very rigorous. We wanted it on firm ground, and so this is the definition that was conjectured back then, and it's still the definition that's used today. We will say that a function is continuous at a point C if and only if three items have to happen, okay? The limit, this is the limit must exist and be finite. The value of the function must exist and be finite. And these two must be equal. The limit must be equal to the same as the value of the function. Again, three things. The limit must exist and be finite. The function must exist and be finite. And they have to be equal to each other. Now that seems kind of, I don't know, bland or forgetful. But once you start to see the genius in the definition, then you start to remember it, because then you start to pay attention and say, wow, that is a really, really well-crafted definition. Let me try to shed some light on why this definition is genius, pure genius. For example, suppose we had this issue here where we had, back in layman terms, you would have to use language like not lifting your pencil, which has so many issues, because what if you're writing with a pen, or what if you're writing with this? That notion is not tight and it's not right. It's good for introduction, which is why I used it, but it's at the end of the day, we can do so much better than that. So the genius in the definition is that it takes care of language like that. The genius of the definition, can you see it? I gotta put it right here where you can see it. No, I'll put it over here. The genius in the definition is the fact that it takes care of language like that. You cannot lift your pencil without using language like that. Instead, it uses language of limits, which is language resting on the intellectual backbone, which is epsilons and deltas. This is really, really tight language. The language of limits, which depends on epsilons and delta definitions. And watch how it works. If you wanted to check that something's continuous, you'd have to go through the checking of the three items. And so I made a little check mark box here, and I want to go through and check. Does the limit exist, and is it finite? So as I approach C, here I am. Here are my y values approaching C, approaching C, approaching C. I've got a right limit. The limit as x approaches C from the right, check. And then I got my y's here approaching from the left. The limit as x approaches C from the left, check. But they're not equal. And if they're not equal, then the limit as x approaches C does not exist. The limit for that does not exist. And so this one, nope. So nope. Whoa, I didn't mean to do that. Let me just scratch it off here. Nope. So fails. So you could stop there and say, well, this is not continuous at C. You see? It uses the language of limits, a much, much more powerful language, to describe a notion that we had to use pencils and lifting pencils and stuff with. That's the genius in the definition. By the way, whenever the left limit exists and the right limit exists, but they don't match, that's a mathematical way of characterizing jump discontinuities. Okay, rather than just looking at jumps. This is a better way. Right limit exists, left limit exists, but they don't match. Okay, then you've got a jump discontinuity. Sorry, I should have said right limit exists and is finite, left limit exists and is finite. They don't match. Jump discontinuity. See, the definition is genius. Okay. Check to see if it's continuous at C. does the limit exist? Okay, as you go from the left, no problem. From the right, no problem. They match and they're finite. Yes, check. Does f of c exist? Nope, it doesn't exist. Okay, then it's not continuous. By the way, whenever the first one is okay, the limit exists and is finite, then if the other ones are not true, then what you've got is a removable discontinuity. Whenever the first one is good, but the other ones are not, that's called removable. That's a fancy way of characterizing removable discontinuities. Try this one again. Does the limit exist? Well, so you go that way, they match, check. Does f of c exist? Yes, it's defined, check. Do they equal each other? No. Whoops. See how the genius in the definition is that before we had to use language like, oh, you have to lift your pencil and put it over here, and then you have to come back and trace the other one. See, that language is not that tight. The genius in the definition is that it makes that language tight. It is based on limits and things that you can verify mathematically. The limit exists, check. The values, the function is defined, check. But they're not equal to each other. That's a fancy way of saying that you'd have to lift your pencil to do that. That's the genius of the definition. It's very, very well crafted to account for all possible strange things that we could never even imagine. Anything that we could imagine, such like this, before we would say you run out of ink or run out of lead or whatever. This has a better way of saying it. You know what? As you approach zero, the limit as you approach zero doesn't even exist. So there, you could stop there. It's not continuous. But the genius in the definition is that it foresees things that we can imagine, and it foresees things that we can't even imagine. I mean, these discontinuities could get as crazy as you want them. The definition is super, super strong. It'll take care of things that we have already imagined and things that we haven't even imagined. And to check that something is continuous, all you got to do is go through the checklist. Does the limit exist? Does the value of the function exist? And are they equal? Let's check this one. This is a famous one. Y equals 1 over x minus 4. It just looks like 1 over x, but it's shifted to the right 4. So it looks like this. And it looks like this. And so let's check the first one. Does the limit exist? Well, the limit doesn't even exist, because from the right it goes to positive infinity, from the left it's negative infinity. It doesn't exist, so you can stop. It's not continuous. And when you have asymptotes like this is called an infinite discontinuity. So there you go. That's the genius of the definition. Of course, probably I should give you an example of one that is. Let's clone this page here. And then let's get rid of this thing. The genius in the definition. So suppose you've got something different. Say you've got, I don't know, something like a parabola. So let's check at 4. Here's 4. Does the limit exist? So you go from the left, you go from the right. Does the limit exist? Check. Is the value of the function defined? Check. At 4 it would be whatever. Check. Do they equal each other? Check. See? What a professional way to say that you can have a little tiny neighborhood that you can trace without lifting your pencil, without running out of ink, and without doing all kinds of crazy things that we can't even imagine. That's how well crafted this definition is. I told you. See why they pay me? Anyways, you can also define continuous not just at a point but over an interval. The trouble with the interval is that the endpoints have to be looked at separately. So let me see. So for example, suppose you have some function here. Let's do a little axis here, and suppose you restrict yourself to this range here from 3 to 5, and you want to know if this function is continuous. What the trouble is that you have to check the limits, and you have to check that they're defined everywhere here, and you have to check that they match. What happens at the endpoints? Well, the only difference at the endpoints, if you wanted to say that the function is continuous over the closed interval, you'd have to just check that at the endpoints, for this one the right limit exists, and for this one the left limit exists. That's the only difference, and they have to be equal to the value of the function at that point. If that happens, we call this a function that is continuous over the closed interval. I don't want to say much more about that now, but I will say much more about that later. Okay, we'll come back to that. Alright, let's do some famous ones. So it's a common question to ask you to check for discontinuities and classify them. So the tangent graph is, of course, famous. It looks like this. What kind of discontinuities do we have? Well, it's continuous everywhere except at pi over 2, at 3 pi over 2, at negative pi over 2, negative 3 pi over 2, etc., etc. At those points is discontinuous. Discontinuous at pi over 2 plus any multiple of pi, and it has infinite discontinuities. That's the type. So check where is it continuous everywhere except here, and classify what type of discontinuities. There are infinite discontinuities. That's pretty obvious. How about this one over here? What I want to talk a little bit more about. This one can be simplified as x minus 4 all over x minus 4 x minus 1. But this is the part that troubles a lot of people, or this is the part that I should caution you about. The minute you cancel these things, you're in fact changing the function. It's no longer f. Now it's a different version of f, because f has holes on here. If you have graph of f, that one has holes in it. But the minute you cancel that, you don't no longer have f. You have one that has no holes at that point at x equals 1. And so that's the thing that you got to think about. In essence, what you're doing when you do this is you're removing the removable discontinuity. You're filling in the hole that it had there. So that's why you should be cautious. You're no longer, these two functions are the same. X minus 4 over x minus 4 times x minus 1. Well, that's equal to, is that equal to x minus 1? Well, almost. You should be cautious. This is almost true. For example, if x is 5, it'll be true. If x is 7, it'll be true. But if x is 4, it's not equal, because this one is 0 over 0 and this one is 1 over 4 minus 1. So it is almost true that they're equal. They're equal everywhere except for that point right there. At that point, they are not equal. So you should be cautious when you graph these things. I think let me think. It'll graph. The graph will look like 1 over x minus 1, which is just looks like 1 over x shifted to the right one.